So here we have a problem where a uniform disk is rotating at 2.4 revolutions per second. Again, before I get started, I'll just get the simple stuff out of the way. What do I know? There's the angular velocity and it's 2.4 revolutions per second. Even before I get into the rest of the problem, I always need angular velocity in radians per second. So how do I solve that? There are 2 pi radians in one revolution. In any one revolution, you would have 2 pi radians. And if that doesn't make sense, I would recommend going to some really good websites that talk about why that relationship exists. And if you do that, you end up with 4.8 pi radians per second. And okay, so now I have information the way we would like it. So this is what they're telling us. A uniform disk turns at 4.8 pi radians per second. It's frictionless, so don't worry about friction. Okay. A rod drops on it, and because the rod was not spinning, now the rod's gonna start spinning. So you kind of took something away, and what's the new angular speed? What's the angular frequency or the angular velocity now in revolutions per second? Okay, they want the answer back in revolutions per second. That's interesting. So with any rotational motion problem, you need to find the inertia, because the inertia depends on the shape during a rotational motion. So if you go to your reference textbook or Google, you can find that, and there's a lot of formulas. And if you look for, well, a solid rotating disk rotating through its center, and you look for that, you would end up with, okay, the inertia of a disk rotated through its center. You can see the axis here, right? Through its center. It says, it also matters where the axis goes through, right? What is it rotating around? It's not rotating around this, right? It's not rotating like this. No, instead, it's rotating through its center. So that matters when you look up the formula. And that is 1/2 mr square. Now, I don't like the picture of this rod, because what I found online was the formula for this kind of a rod, a circular rod. But they have over here is this rod, and I couldn't find the inertial formula for a rod like this. These are two very different shapes. So I just imagined maybe they didn't mean to draw this one, and they were meant to draw this one, just didn't realize it. So with that assumption, I've got the inertia of the rod, of a circular rod, to be 1/12 mr square. You can get that from right here. Hopefully you can see it on my screen over here, the last one in this row. And where did I get the formula for disk? Doesn't matter, but you can find it anywhere. It depends if you find the right place. Here, this is good, right? So hopefully you can see that here, solid cylinder with a very thin height, with the axis going through its center, 1/2 mr square. Okay, so now that formulas are out of the way, we have the inertial formula for disk and inertial formula for rod. We can say, hey, what do we know? What are some basics that are given to us? Well, if this is a bit technical, if sum of the torques is 0, right, then the change in angular momentum is 0. Rotational momentum is 0. So what does that mean? Ultimately, it just means whatever the momentum of the spinning disk before is the same as the momentum after. So what was the angular momentum of the disk? What was the angular momentum of the rod? Is the final angular momentum of the disk and the rod together, right? So, well, the rod was not really spinning, so it really didn't have any angular momentum. That was 0. The disk was spinning, so, and it has 1/2. So the formula for, I'm just going to name this squared. Actually, let me see if I can simplify this for you guys. So what is this, right? It's basically 1/2 inertia times angular speed squared. That's L, right? So now we're going to think about the disk. What is it for the disk? Well, it's 1/2 again, I times w squared. And the formula that you'll substitute for the disk is this one. And the formula you would substitute for the rod would be this one. This one, sorry. This one, right? Inertia of rod and inertia of disk. Just the formula are different, but otherwise, the generic equation is the same. Okay, with that in mind, we start over again. So here's the, I'll call the rod just the disk 1, and I'll call the rod number 2. And then I'll just say it's the sum of 1, 2. So, well, this is 1/2 inertia of disk times the speed, angular speed of disk squared. Alright, and 1/2 inertia of the rod and the angular speed of the rod squared. Now, this is going to 0. There is no angular speed. The rod was just dropped flat. And here's the inertia of the disk and the rod together, the angular speed of the disk and the rod together. Right? Now this all goes to 0. That doesn't, because you multiply by 0, you get 0. So what you have is inertia of the disk, angular speed of the disk is equal to the inertia of the two components together and the speed of the disk and the rod together. That's what we're solving for here. With that in mind, let's start substituting. Here we have 1/2, and inertia of the disk is, we found it to be 1/2 m. Oh, by the way, we can cancel out these two 1/2s. They're gone because they're both sides. So let me just clean that up. So with that in mind, we're starting with I of d wd squared equals I of disk rod w disk rod. That's what we're trying to simplify. So I of d is 1/2 mr squared, mr squared times wd squared, right? And on the other side, it would be the sum of the two, mr squared over 2, that's this one, sorry, that's this one, plus 1/12, which is mr squared again over 12, right? That's this one, w dr. So now I've substituted everything there is to substitute. Now one thing I want to call out is it's not r squared, actually it's l squared, the length, because it doesn't think of it as the radius, it thinks of the entire length, which is really the diameter. So we're going to fix this here, l squared, not mr squared, but we're going to substitute that out really quickly. So first let's get rid of m from all sides of the equations, right? Gone. So I'm left with r squared, radius of disk, of course, angular velocity of disk over 2 is equal to r squared over 2 plus, and let's think of the length as 2 times the radius, right? So 2r squared over 12 wdr, angular speed. Okay, and what do we, well, looks kind of starting to look complex. Let's just get rid of 2 from all sides, 2, and this would become 6, and 2 1s are 2, 2 3s is 6. So r d squared w d squared equals r squared plus, actually it's 2 times 2, 4, so this was 4, so 2 is still left here, and this becomes r squared, so it's 4r squared. And let me clean that up. So it was 2r over here, it was 2r squared, which became 4r squared, and over here we had 6, so this becomes 2, this becomes 3, and w d r squared w squared equals r squared plus 2r squared over 3 w disk and rod. This is radius of disk, this is radius of rod, this is disk, this is disk. Okay, let's keep going. Starting to look complicated. So we got pretty far. If you simplify it further, well, you could take this, and really what we just want to find is, I'm going to take this down where there's more space. So we're at this point. I'm going to clean it up. Is equal to radius of rod squared W disk rod squared. So this is what we're looking for. So let's get everything on one side. I'm going to get this on one side, right? W, and just divide the other side by the entire thing. That looks scary to me. I don't know about you. And if you solve that, well, the radiuses are actually the same. The radius of the disk, they actually said that they're equal to the distance. So the radius of the disk and the radius of the rod are one and the same. If that's the case, we can drop this D and the R. So W square equals R square. Everything is the same, so let's just call it R. WD square, that's still a different thing. So R square plus 2/3 R square, if you do the math on that, 5/3 R square, right? And if you simplify further, that's the same as having, well, R square cancels out, and then that becomes 3/5 W d square. So all of a sudden we have W, which is the angular velocity of the disk and the rod together, squared is the same as 3/5 of just the angular velocity of the disk. So what happens is, the disk was spinning, it was happy, and you added on a rod, so now it's carrying the load of the rod too, so together it's 3/5 less than that. And if you get rid of the squares and you look at that, then you will end up with W squared. Let's see how to do this. You could start substituting. We have 4.8 pi radians, right? So we can put that in here. What is 3/5 of 4.8 pi, right? Squared, and then square root the whole thing. What's this value? We can look at that. And that should come out to something like 1.44. Well, actually it'll come out to 2.88 pi radians per second, and you could convert that to get 1.44 revolutions per second. How did we convert that? Well, 2.88 pi radians per second multiplied by 1 revolution, every 2 pi radians. Radian goes away, pi goes away. So you have 2.88 divided by 2 revolutions per second, and that's 1.44 revolutions per second, and that's what they asked you. What is the angular frequency in revolutions per second when both the disks are together? And you found this. All done. Thanks for watching.